all right? She was okay. And right on time.
I think everyone's been waiting outside just to come in too.
Well, welcome to the Complex Systems Seminar. We have today Braden, our PhD student, with us. Our meaning our group, not mine.
You've been disowned with insect to the seminar stuff.
As we all know, so this is the final talk in his PhD. This is his whole work. As we all know, basically you are an adult in academia if you have a PhD. And so Braden is going to tell us how he wasted his youth. There you go.
What an introduction. Yeah, thanks everyone for coming down. I am aware I am the very last thing before most people's long weekend, so I appreciate so many people showing up. So talking about what I've been doing in my PhD, which is all revolved around this idea of a reservoir time series analysis, which is a term that probably means very little without a decent amount of background, so I'm going to jump straight into that. So most of the work is revolving around this idea of a reservoir computing. So the idea here is we're working in this machine learning type framework where we've got time series coming in, we're doing something to it, and then we're trying to make some prediction coming out the other end. Now, often when we think about this, it's usually from more your computer science standpoint, where you have something like a recurrent neural network or something where you've got these large number of parameters, which you can then train individually to try and get as close to the desired output as you want. So where reservoir computing comes in is because tuning a large number of parameters is quite difficult, the idea here is if we actually make a more sophisticated choice about how we do our information processing, we can greatly simplify what we actually have to do when it comes to our training process. And what that looks like in practice is we choose our information processing center to be some sort of dynamical system. So here we can represent it in continuous time with, say, some flow f over our reservoir states, which are typically high dimensional. We have some input here, which we're considering just to be a scalar, although you can also consider multivariate with just small modifications, where u here is considered to be some observation of a dynamical system. So there is actually something happening in the time series that is interesting and facilitates prediction. And then we've got some collection of the parameters of the reservoir v, which could be matrices in the case of a network, or something more complicated if you're looking at, say, agent-based model type network. So that's your continuous time. More realistically, we're going to be working in discrete time because often our observations are real data where it is discretized in some way. And so that's the sort of formulation we'll be using a bit more going forward. So why we care about this and why that simplification matters is because once we've picked our dynamical system, we keep it fixed. So we don't have to worry about changing that at all. We can just feed it with the input and let it go. So the only training then is from these high dimensional states to whatever our desired output is. So typically through some readout function here, g, mapping to whatever our prediction is, y in this case, where r is now collecting just the parameters related to our readout. And because that's the only learning that needs to be undertaken, and because we were sophisticated in how we chose our system originally, we can actually choose this readout function to be incredibly simple. And usually it's just a linear readout function, which then can be computationally simple through just linear regression, typically with some sort of regularization. So the example I'm going to use throughout this work, and probably one of the more well-known examples of reservoir computing, is an echo state network, which dates back to some of the seminal work in the early 2000s by Jaeger. And it's a nice one because it's actually easy to visualize because it's somewhat similar to things we've already seen with recurrent neural networks. So the idea is you've got your input, there is some vector which coordinates feeding that input into your network of nodes. So typically a large network with a large number of nodes to facilitate that high dimensional activation state. Information then passes between the nodes based on some adjacency matrix, which is our VADJ up there. And then that can be read out through this vector here, determined through linear regression to our desired output y. So that function up top there is just our activation function, which tells us how the information is propagating through our network subject to our driving signal. And v-bias here is just a bias term, which is sometimes included as part of the definition. So why does it actually work? So there's a couple of key properties we look for in a reservoir computer that tells us it's going to be decent for one of these sort of tasks. So the first property here is the fading memory property. So what we expect is every state of reservoir computer has memory of the previous states due to the, well, in the encapsulated network case, this adjacency matrix gathering information from previous nodes. But importantly, its memory of those past states fades the further we look back in time. So to sort of understand what's going on in these figures, I've taken an encapsulated network and I've just fed it with standard Gaussian noise. And all I'm looking to do is I'm just trying to predict the previous value of that Gaussian noise. And I'm measuring my error based on some correlation. So if I've got no delay between my input and my output, obviously we get a perfect correlation. It's got the memory right there, it's just been fed in. The further in the past we look, the faster that the more that correlation drops off until essentially we've got no correlation because we're feeding in standard Gaussian noise. If I run a cumulative sum over that, I get this profile here and we can approximate what's called our memory capacity. So this is sort of demonstrating this fading memory property, that we lose memory of past states the further back we look. From there, because we are forgetting past states, it means that whatever our initial state of the reservoir was, which was independent to our driving signal, over enough time we're actually going to lose the memory of that initial state, which gives rise to our consistency property, which is that if we have two reservoir computers, different initial states, and we feed them with the same input, eventually they will converge. What that looks like is our activation states, and I apologize, that should be a t+1, which is some kind of complex function of all the previous states, simplifies to some function of just the most previous inputs. So some finitely many here represented by this M fading memory property. And for those of us who've worked in nonlinear time series analysis for a while, this hopefully looks a lot like a form of delay embedding. And in fact, thanks to some of the more recent work by Alan Hart in the US, we've now got the proof to show that it is a form of delay embedding. And that means that the activation states we're getting out are in some way in good approximation to something to do with the original system, which is facilitating a lot of the tasks and the success that we're seeing through reservoir computing. Now, so far, a lot of the reservoir computing is just leveraging that for supervised learning tasks. But for those of us who know about delay embedding and what it's been used for historically, is there's a lot more that can be facilitated by having a good quality informative embedding. And that's sort of where my work is coming in. How can we actually take these ideas from the supervised learning environment and transition them into an environment that is not so interested in just being able to have a good prediction of some future state or a different series? Which brings me to sort of reservoir time series analysis, which is our proposal of how we're actually going to overcome these issues. So I'm going to talk into two parts. The first one is going to quite quickly go over what is reservoir time series analysis, a bit about why we should care about it, what it's looked like historically and what we're proposing, leading up to this idea of complexity with reservoir time series analysis, which is sort of our main contribution in terms of what RTSA can look like. And the second part then, which you consider very important, is, well, if we can then develop unsupervised methods for it, what does that look like? And some actual tasks trying to kind of cover that framework. So if we think of reservoir computing as the study of the reservoir states for supervised learning tasks, reservoir time series analysis is the more generalized task here, which is just generally trying to infer information about the underlying system from the states. So we can think of this sort of Venn diagram. We've got reservoir computing here. Reservoir time series analysis is sort of this all-encompassing field. And the way we approach it is we think of the end result of a reservoir time series analysis method is going to be some feature. Now this could be scalar, vector, multivariate. It's really dependent on context, but the idea is whatever this feature is actually tells us something about the underlying system. Now, a bit about why we should care about it is we've already seen very impressive past results from reservoir computing, both in forecasting tasks, which can be an indicator of good embedding quality, and classification tasks, which gives us an idea that there are actually informative features there to be generated. They are very simple to generate, as relative to some of the more difficult parameter tuning you have to do with regular embedding models. So, for example, with the encapsulated network, we really need a reservoir size, the idea being the larger the better, but it'll take longer to compute. Some connectivity measure for the adjacency matrix. Sparse is usually the heuristic we use. And some scaling of the adjacency matrix to ensure we're getting reasonable dynamics, which here falls into just scaling it so it has a certain maximum absolute eigenvalue called our spectral radius. Tuning these parameters, we've got good heuristics for, and we're relatively confident doing it, and it can be done in a simple way. Other reason we care is, while so far I've sort of talked about digital implementations, you can absolutely use physical dynamical systems as well. So that's, electronic circuits, similar in the case of photonic. This is a case here of a mechanical system that can be used as a reservoir computer. And I mentioned spin waves because there's actually a group over in physics looking at reservoir computing with that sort of stuff as well. And that facilitates much faster computation over your digital implementations as well. So there's a number of reasons we care about these sort of models. So what does reservoir time series actually look like in terms of feature generation and what you're going to get? So one of the earliest ones we started with, probably the conceptually easiest to understand, is just a time average activation state. We feed the reservoir with a signal, we get our high dimensional activation state, and we just average them over time. What we're getting here is essentially the average response of this reconstructed attractor in this reservoir space. And why we're interested in this one is because it's actually seen use in previous works. It's been used as a feature for classification in spoken digit recognition and other speech tasks. And we've also actually used it in some of our previous work looking at extracting parameters from mechanical systems. So we have some understanding here that these features are actually useful. So to sort of get an idea of what we're looking at here, I've got a bifurcation diagram of a logistic map, and I've just scaled it so it's all contained in the unit in the range -1 to 1. And here I've got a realization of a mean activation feature tracking along that same parameter axis here. So what we're really trying to see is, do these features respond to the varying dynamics we see in the system? So for example, we've got periodic beta here, transitioning into chaos with some intermittent periodic windows. And if we track along here, it's somewhat hard to see in this case, but we do see that some of these periodic windows are appearing here, and we do see these gradual transitions as we increase our parameter value. So that's really what we're looking for, features that are responsive to changing dynamics in the system. So next step might be, well, let's look at, say, higher order moments. So next one we looked at was this covariance feature. So same sort of thing, we're looking at the covariance between the various nodes in the reservoir. The output of this one feature is a matrix, but it can be easily rescaled to be considered in vector form. So following that same sort of example, we can still see the appearance of this window here, admittedly at a much finer level. But what's interesting with this one is, whereas the previous case I was using a 100 node reservoir computer, here I was just using 14 nodes. So you get much larger dimensional features out of a method like this, which can be beneficial for certain tasks. So moving to more sophisticated features, one interesting area that popped up in reservoir computing research was this idea of model space representations, which is the idea that if you feed a reservoir computer with a signal and you train this readout, well, the reservoir computer together with that readout is in some way representing the underlying system. And so by analyzing the readout vector from that, you actually get an idea of what the underlying system looks like. So as another feature, we could simply consider these readout vectors. So I talked about how when we're typically doing our training, we keep it very lightweight. So here's how we calculate it. It's just linear regression with some regularization parameter here, beta, which in some ways is designed to prevent overfitting in the supervised learning tasks. But here we can just consider as somewhat a free parameter that we can vary as we require. And we look to actually see, all right, well, how do these respond as we vary our parameter? Now we just focus on two cases here. We first of all focus on the one-step prediction, which is the most common one, because with a one-step prediction, you then have enough information that you could run your reservoir computer autonomously by make a one-step prediction, feed it back in, and you get a realization of what your time series could look like. And also the auto readout, so training back to the input that just came in. In some way, this is a measure of how distorted the signal is when it's fed in, becomes when it's fed into the reservoir. And what we notice is, so this is for the auto readout case, suddenly these periodic windows, well, not suddenly, but these periodic windows are now becoming far more evident, and the transition over our range far more obvious. If I go to the one-step prediction, the contrast here is larger again, and this is sort of a reconstructed bifurcation diagram, so running in that autonomous mode. And we can see that we actually are getting most of the structure in that bifurcation diagram. That's sort of capturing this idea of being the representation of the original system. So we started with those features because those somewhat had a connection to ones that have been seen in literature and captures sort of the idea of what we're after with reservoir time series analysis. Informative features that in some way respond to the dynamics and can be used to infer meaning. The issue is most of those are hard to infer meaning in and of themselves. It's really more in comparison to other features. So what our next step was can we actually develop a feature which in and of itself is somehow representative of the underlying system? Which got us to this idea of complexity. So the idea here is we want to develop a scalar feature, which in a similar way to more theoretical measures like your Lyapunov exponent, gives us an idea of what the underlying dynamics of the system are. So from periodic to chaotic through to random. There's a couple of conjectures we started with as a beginning point leading up to this feature. The first was that if we have a reservoir computing framework, and we're looking to make a prediction task, if we have a complex signal, then the task of forecasting the future values is going to be harder than if we, say, had a periodic signal. Yeah, periodic signal we'd expect even without the reservoir computer we can make a prediction easily. Something chaotic, it becomes much harder. And random, it's near impossible. You're trying to predict something that is random after all. In reservoir computing specifically, hard tasks manifest in a greater use of the information within the activation states. So if we had a way to measure that use of information, we would have a way of determining how complex that signal is. And our argument is we do have a way of measuring that. It's again coming down to those readout vectors. They are, in the presence of regularization, determining how much of the information from the reservoir we actually have to use when making those predictions. So what I have here is a number of readout vectors. I've just sorted them by their vector value and put them on a log scale. So this case here are all periodic signals or a constant value signal, and we see this nice ordering as our periodicity increases. Here we have all chaotic systems, and importantly, we know that even the least chaotic of these is generally greater than the highest curve we saw here for our periodic case. Here we've only got IID noise generated based on a number of different distributions just to sort of get an idea. And all of these generally present higher curves than the chaotic case. So already qualitatively, we're able to see this ordering of the chaos of the underlying dynamics. And rather than try to find some really complex way of reading this out, well, we could just look at an area under the curve here. And that should give us an idea then of how we can sort those dynamics. So here, just using a trapezoidal approximation to keep it simple. And only caveat I'll mention here is we've got this I here, which again corresponds to our how far in the future we're willing to forecast. We're just going to focus on two cases, the one-step forward forecast as before, and the zero-step forecast, again as before. The meaning behind the zero-step one here, which we call the auto-complexity, is somewhat vaguer because we're not trying to forecast values, so it's not necessarily measuring how difficult it is to learn the system, but it is measuring how difficult it is to reconstruct the system after the transformation of the echo state network. We weren't necessarily sure if this is going to respond as favorably as the one-step prediction, which is what is presented in these curves, but we were willing to explore it. So looking at the logistic map here, I haven't scaled it to the range -1 to 1, but so the variance is actually naturally built in. Here we have the Lyapunov exponents, where what we're really looking at here is where we cross this value of 0, which is our transition from periodic to chaos. This is our auto readout, and this is our one-step readout, complexities rather. And what we can see is a very, very high correlation between the transition points here and these changes in our feature value vector here. So there is a high correspondence between what we're trying to establish and what we have. And importantly, this one really required knowledge of the underlying system to be able to reconstruct. This one is constructed from data alone. You can do a similar thing for the rest of the system. So here I've now just got my approximation of my two largest Lyapunov exponents. Again, my two complexity measures. And while it's rougher in this case, we can still see key features emerging corresponding to the transition changes here with your periodic window and then your various periodic behavior. So one final thing on these ones actually. So we did a little bit more here actually assessing height parameters and how these varied with respect to those. One of the interesting results was if we take the limit as the reservoir size gets really large and the limit as we have large length time series feeding in, the variance in these features essentially becomes negligible, which is a big result here because it means that we can have different realizations of the same system, and as long as we've got a sufficiently large reservoir and long enough time series, we should be getting the same complexity measure every time, which is big then for being able to use these as an actual a measure that is invariant essentially to those variations in when we're taking our observation. So that's sort of what reservoir time series analysis is looking like. Those are the sort of features we're getting out, and that's sort of where it's come from. So how can we then actually go about utilizing these in a way that is separate to the supervised learning environments that have been looked at so far? So the first task we looked at was a relatively sort of a first step we considered for these sort of methods in this signal distinction task. And really what we're trying to assess here is, can we actually say that these features are able to separate one signal from another if their underlying system is different? If they're not able to do that, we expect that any more elaborate tasks are going to become quite difficult. So the idea here is we've got two systems, our reference and our comparison, and we assume that we're actually able to generate sufficient data from both systems. How we approach assessing this is then we generate a large number of samples from the reference, a large number of samples from the comparison, we calculate our features and we calculate the distance between those features. In the case where we're just taking signals from the reference, we'll get some distribution that looks like this. Yeah? They're all from the same system, so there'll be some error based on our sampling, but they should be relatively close to 0. When the system is different and we start taking differences between our features, we should see a larger difference emerging because they are from a different system. So this is an ideal case. If the feature is not responsive to the signal change and not able to distinguish the features, we see this overlapping in the distribution of our distances here. So from these then we can derive some statistical measure. So here what we say is, because we're taking pairs, we compare the two, and we just count how many times the comparison distance is greater than the reference distance. We repeat this 100 times, and that gives us a statistic of how well it's able to distinguish the two signals. By then choosing particular systems and particular signal variations, we can assess where these features are useful in distinguishing and when they're not. So obviously it's going to be helpful if we actually have some other features from other nonlinear time series analysis areas to compare to. So I'm not going to go into these in too much detail simply due to time, but the main ones we looked at was ordinal network analysis, which is sort of two fields in one. On the one hand, it is looking at ordinal partitionings of our time series and the symbolic dynamics. And then also, if we think of representing those as a network, we can then bring in a number of network measures as well. So the idea here is I've got an embedded version of my time series. I am in some way partitioning this based on the ordering of these dimensions. This gives me a series of 6 symbols. If I look at how those symbols transition to each other, I can represent that as a network here. So typical measures in that space are things like your permutation entropy or conditional permutation entropy. With the network, you can then look at things like your path length measures, etc. Alternatively, we could look towards topological data analysis and persistent homology. The idea here is we think of our data as in our embedded space as some point cloud. If we now imagine we're growing balls around the points in our point cloud, we look to see when components become connected, where we begin to get holes appearing, and we can represent that in some way as looking at the birth and the death times, and then the distribution of features in this space tells us something about the underlying system. Finally, one we look at, we spent a bit of time looking at, is recurrence quantification analysis. So the idea here is if we have a signal and either in the original signal space or in the embedded space look for when that signal passes by previous values, we can then give it a 1 when they pass close to each other, or 0 if they're not passing close to each other, and we can represent that in some way with these 2-dimensional recurrence plots. And then the features in these recurrence plots, if we look at the distribution of them, tells us something about the underlying system. So for example here, we've got random noise, a sine wave, realization of the logistic map, realization of a Lorenz attractor, and for example, when you've got something periodic, you get these large diagonal lines appearing. Random noise, it's mostly sporadic dots. Logistic map, we do have diagonal lines, but the distribution is clearly different to in the periodic case, and similar to the Lorentz, some diagonal structures here. So diagonal structures are one of the ones we look at. Vertical line structures are vertical voids as well, so gaps between recurrent points. All of these structures can in some way give us information about the underlying system. So we've considered various number of features from those different areas, and these are sort of our results towards that. So we considered two systems here which were just looking at variations in the mean and the variance of Gaussian noise, and then these ones are for varying parameter values in a logistic map, Russell system, and Lorentz system. So these cases here are all multivariate features. These ones here are just the distributions of some of the structures I was talking about. And these ones here are the 4 multivariate features that I talked about with regards to reservoir time series analysis. And probably one of the earliest things we notice is that particularly the reservoir covariance performs particularly well, but in general we see an improved ability for the ecosystem network features over the recurrence quantification analysis features here. Chaos transitions, yeah. We also consider a large number of scalar features, so again some recurrence ones, but here's where we also have our ordinal network analysis and persistent homology, and here are our complexity features as well. And what begins to become really apparent is that a number of the existing nonlinear time series analysis methods are not particularly sensitive to changes in the statistics of the underlying signal, whereas the reservoir computing features remain so. But also the reservoir computing ones are generally sensitive to the various chaos transitions we see across the 3 systems, whereas most of the other methods seem to struggle in most of the Lorentz case, but even some of the other cases as well. What might be alarming at this point is that another feature that did particularly well is this one here, which is just if I track the standard deviation of the 2 signals coming from the different systems. So we might be inclined to say, well, maybe the ecosystem network is just sensitive to change in the variance. So motivated by that, we had a look at a number of surrogate systems as well. So rather than the difference between 2 trajectories of different systems, here we have our reference case as a signal from a system, and the comparison case here is a surrogate generated from that. So the surrogate allows us to control exactly what attributes of the signal are conserved between the reference comparison case. So importantly, in this case, which is a random shuffle surrogate, we are intentionally keeping the mean and the standard deviation the same between the 2 signals, but removing the deterministic aspect. And we would expect that all of our nonlinear time series analysis features do quite well in this case, but even amongst them, the reservoir computing ones tend to do particularly well. And this is in a case where we are intentionally preserving the statistics of the signal. Another case here is amplitude adjusted. So here, same sort of thing. We are preserving the mean and standard deviation, but we're also preserving the power spectrum. And again, similar results with the reservoir computing ones doing particularly well. The final case is a pseudo-periodic surrogate. In this case, we're sort of trying to keep the delay embedding of the attractor the same, while still giving us a surrogate which is not, so it is a stochastic process, it is not a deterministic system. In some way, this is sort of, we only consider it here as a trick case, which should be difficult for certain dynamical system methods. But we found that actually most of the dynamical system methods were able to handle it quite well, with, again, reservoir computing ones doing especially well. So the outcome of this is essentially we are able to show that the reservoir time series analysis features that we were looking at are particularly sensitive to changes in dynamics. So from this, that motivates us then to say, okay, well, where can we actually push this to a task where it might actually be more interesting than this very abstract, take 2 realizations, see if they're different case. So one of the ones we looked at here is what we call a recurrence preservation task. So we're thinking here in terms of the recurrence quantification analysis field I introduced a little bit earlier. And when generating these recurrence plots, a usual first step is to generate a delay embedding, and then from that, generate your recurrence plot and go from there. Now, the hope is that by generating the embedding, we are somehow getting something close to the original state space, so that the recurrence plot is reflecting the information in the original system. Now, in reality, if your embedding is not going to be able to capture the original system perfectly, so there will be some discrepancy in the recurrence plots you get out. So we were interested to see is, well, if we use an echo state network embedding instead, are we in some way able to preserve more of the characteristics of a recurrence plot than if we use a delay embedding? So somewhat a novel task. We hadn't found too much that explored it specifically in terms of which embedding technique is better in this way. So we looked at a couple of different methods to how we can actually measure that. The first is essentially trying to say, well, we want to preserve everything in the recurrence plot. So here we are point-wise comparing the points in the original recurrence plot, which here we're going to assume is from the original full state space of the system, and the reconstructed one, which is an embedding of an observation. And point-wise comparison, and then some ratio between how many of the points aligned and the total number that we expected. Now that's somewhat a, we could call it a harsh metric. We'd expect that a lot of the embedding methods are going to struggle to get a good joint recurrence rate fraction. And realistically, we're not necessarily interested so much in preserving all of the recurrence plot. What we're more interested in is, does it allow us to reconstruct the features we're interested in sufficiently? So rather than looking at the whole recurrence plot, we may just look at individual scalar features calculated on those recurrence plots. So similar to the ones we looked at earlier with the signal distinction task, we could take two of those, realize from the different recurrence plots, and then compare those through, say, some absolute deviation metric. But again, we can come up with scenarios where we could get the same scalar features out, but the actual structures in the recurrence plot are different in some way. We could devise pathological examples to demonstrate that. Instead, what we argue is that what actually is important here is the structures in the recurrence plot, the diagonal lines, the vertical lines, and their distribution. So rather than going to either extremes, we can take some middle ground here and actually look at the distances between those distributions. And we've got distance measures defined on distributions to then measure that discrepancy. So I've sort of talked around a little bit, but one of the secondary objectives here was to actually explore sort of what is the role of embedding in recurrence plots. So there are arguments for generating recurrence plots with no embedding at all, just from the raw series, and there's a lot of arguments for actually no embedding is important. So we considered a range of different embedding techniques here. So no embedding, as mentioned, uniform delay embedding, where we look to take a delay time and a dimension, and we can just take intervals of that delay to generate an embedding vector. We've got a number of non-uniform delay embedding techniques, where here we're looking for particular embedding lag, which we hope correspond to important timescales in the signal, and our reservoir space embedding, which is sort of our proposal and is very new to this sort of area. So as a first example, here we have a Lorenz system. So here is my three-dimensional state space of the original system. So this is my full state space before I've taken any observation. We can see some sampling artifacts there because we didn't want to sample it too smoothly. We feel this is a more realistic representation of what you might see from data in real applications. This is what our observation looks like. So here I'm just taking an observation of the X component, so one of these components here of this system, and then my various embedding techniques. So a uniform delay embedding. This is my first non-uniform one in the percusal. A maximum derivative on projection, which really struggles, we feel, because it is not a smooth sampling of our attractor. And here are my first three principal components of an ecostate network embedding. And we can see that some of the structural elements are preserved in the percusal, uniform, and ecostate network. What we're interested in is which one is preserving them best, essentially. So here are the corresponding recurrence plots, and we begin to see some of those differences already manifesting in what the structures look like. So for example, when we just take the signal, we get these sort of back diagonal measures here because we don't actually have a sense of whether we're moving forward or backward just from a signal alone. We see the maximum derivative on projection has similar things, but also it fails to capture a lot of the fine details in where the diagonal lines are appearing. But in general, between the uniform, percusal, and ecostate network and the original, they actually are quite similar and capture a lot of the details. We did a similar thing with the RTSA system. So similar sort of observations, particularly struggled, generally okay from these three, maybe a bit of warping the ecostate network case, which might make us think that one's not going to be quite as suitable. And similar results here for the recurrence plots as well. So actually going to quantifying some of these results, what we found was interesting. In general, our overall conclusion was that the Purcell embedding is generally the best at preserving the structures in the recurrence plots across most all measures and across both systems. The rest of the ones, results I'll put up in a second. What was interesting though is that the XSA network is not that much worse, and in some cases does seem to offer somewhat of improvement. Looking here, for example, the variance in the XSA network is significantly lower than the Purcell. So there might be something to dig into there about why there are some examples here with a Purcell embedding where we seem to get a really bad representation of what the recurrence plot is. They're fairly comparable across a lot of the other measures, Purcell narrowly winning out in some, but there are cases here where the XSA network also does particularly poorly. For example, here with the entropy of diagonal line measures. One big conclusion to take away here with regards to our secondary objective is all of this does indicate that some form of embedding is typically better than no embedding. So we can see that as, in general, the no embedding case is typically worse. Obviously the uniform one did particularly badly there, but that's really the only case where we see it struggle to beat the no embedding case. And similar results for the reversal system. Yeah, here the advantage of the Purcell embedding over the XSA network is a little more pronounced. Yeah, so it wasn't a big win for reservoir time series analysis. This wasn't the key to unlocking recurrence plots and sort of opening the door to this is the way to be doing it in the future. But it does show that there are potentially use cases for this sort of embedding in pre-existing nonlinear time series analysis fields. And we looked at recurrence plots here, but things like topological data analysis and ordinal network analysis are other areas we didn't really look at, but it could be somewhere where you could push these methods where they might be able to have value because of the type of embedding we're getting out. So the final application we're going to look at here is concept drift detection. And I'd be remiss not to mention that this was one of the motivating factors behind the PhD. So part of what I do is I'm connected with the Center for Transforming Maintenance through Data Science, and originally when we pitched the reservoir time series analysis, our comment was this could allow us to better detect changes in signals from machinery, essentially. So the idea of this task is we've got some time series coming in real time, and what we want to do is we want to be able to detect at what point does the system underlying that signal change. And our motivation in terms of the center was this could be an indicator of, say, when an asset is breaking and allow us to do, say, preventative maintenance, that sort of idea. So I mentioned maintenance here. It's obviously got other applications in areas such as medicine, and it's typically comes from a background in computer science where the idea of concept drift is the data underlying your model has changed, you need to stop and retrain your model. In terms of this particular task, there are a number of ways you can actually measure performance here. I'm going to bring up 3 here because these will be the 3 that I will look at. So if you've got a time series coming in with a number of drifts, the obvious first measure you look at is, well, how many of those drifts did you actually detect? That's your true detection rate. That's obviously only going to get you so far. A method that detects a drift all the time will get a perfect TDR, but it's going to be absolutely useless in practice. So you also want to then look at the number of false alarms, and you want that to be as low as possible. And even then, even if you get a perfect alarm every time, if it takes you too long to detect it after the onset, it's not going to be useful either. You can think of probably a very bad case in medicine where they're having a heart attack, but you detect it too late. Even if you detect it perfectly, it's not useful. So we measure that with our mean time to detection, and we want to keep that as low as possible as well. So traditionally, this was very much a statistical task. So its origins sort of with this Page-Hinckley test, and we've seen from there this movement to window-based statistics, adaptive window particularly being one that continues to see use. More recently with sort of the popularization of Bayesian statistics, there's been a number of Bayesian methods approaching it as well. But what we've sort of observed is that as this idea of thinking of time series from dynamical systems seems to have grown in this community, we have seen a bit of a surge in dynamical system methods. So for example, recurrence quantification analysis has seen application in the concept drift task. So have network-based measures, so has persistent homology. So the methods we've already talked about as comparisons have already kind of made their way into this field. This felt like then an appropriate place where we could try to move reservoir time series analysis. And also in doing so, we could try to actually sort of unify these frameworks we're seeing for applying dynamical system approaches to concept drift detection, because somewhat at the moment they are quite sporadic and dependent on the different analysis area. The way we see it is we're looking to apply dynamical system methods to the concept drift task, what we're really looking to track is the complexity of the underlying system. And what we're looking to detect is when does that complexity change, because that's our indicator that the underlying system has changed. In that way, we can then set up an approach where you have some window, we're calculating the complexity on the window, and we're moving that through our time series, and we're looking to see when our measure changes. And importantly, that change in our complexity measure should look like a statistical change. It should be an evident transition. So to sort of give an example of this, this is a very long realization of a logistic map. And all that's happening is between these yellow and green regions, I am making a change in my bifurcation parameter of the system. Now these are all chaos-chaos transitions, and I'm applying some sort of scaling in between to keep the range -1 to 1. But the immediate transitions here are not evident. However, by tracking my complexity feature, which here is my one step forward complexity, suddenly those transition periods are made evident, and they're made statistically clear. So we could then take the existing statistical methods, such as an adaptive windowing approach, apply it over this series, and we should be able to detect all the drifts very easily. This is a particularly nice case with a very large window length, which is why we see this really long transition period here. And in general, we see quite nice results for it. Now, standard deviation still does quite well because although the range is -1 to 1, the actual variance is changing quite a bit, but we see most of the methods are able to converge quite well, and particularly our reservoir computing methods here, which are the dark blue, both able to detect all the alarms in the long run. They tend to have low false alarm number and generally do surpass many of the other methods. So here the persistent homology actually did quite well as well. This one did miserably. And also low mean time detection and low number of false alarms. So the reservoir computing ones do seem to be outperforming some of the existing nonlinear time series analysis methods in this task. It's promising. Now, it wouldn't feel right to not include some experimental data, given our motivation was experimental. So here's another case we have here, but now rather than a system with a varying parameter, what I have here is a bearing. And the green regions here correspond to a healthy state, where the bearing is operating normally, and the yellow here are all different fault modes induced on the bearing. So there's a couple of faults in the outer raceway, some on the inner raceway, and one on the fan end as well. And what we see then is, again, tracking this complexity feature, we see all the healthy states have roughly the same complexity, and the various fault modes have different complexities, and we can detect those changes then by running over the top. And this is one case where the reservoir computing methods really began to shine. And we see it was only really 3 methods that were able to detect all the drifts. And amongst those, there were the first 2. And there's our reservoir computing one. So generally kept a lower number of false alarms. And most of the mean time detections are pretty comparable here. If we had to be critical, we'd say it did perform slightly worse than one of the other ones that managed to detect all of the drifts. Now, it's not perfect. We can certainly see that we might have some difficulty here, because how do we say that's not a statistical drift, but that is? But they do seem to be able to at least keep pace and in some cases surpass existing nonlinear time series analysis methods, which is, yeah, what we were hoping to see after all this, that there is actually some benefit to looking at reservoir time series analysis over another analysis methods. So sort of as some final comments, yeah, we've discussed reservoir time series analysis. I'm hoping that at this point people at least have an understanding of what it is. There's a lot of details underneath it that I sort of brushed over because for sake of time. But the main takeaway is that it's this broad field that encapsulates the existing reservoir computing methods and tries to allow it to branch out into other areas that it has not seen application to yet. The main method we looked at was this reservoir computing complexity, which we believe is an interesting feature which warrants further development, particularly because it is quite responsive to the underlying dynamics of the system, and we could use it to infer information in a number of cases. And we also looked at some actual applications of it, where it was able to perform existing nonlinear time series analysis methods. There's a lot of areas for future work from here. Obviously, this is just sort of introducing the idea of unsupervised learning tasks to the idea to reservoir computing, and there is a lot of unsupervised learning tasks which we are free to explore. There's also a lot of other areas where embeddings are currently used, and potentially reservoir computing embeddings could offer additional improvements in that case. I'm highlighting just a couple here of areas that appeared in my work, which I thought interesting. So these are very similar curves to the ones we saw before for reservoir computing complexity. The only difference is these are using a single node delay coupled Mackie glass node in an electrical circuit as the reservoir computer. It's one I implemented myself, so it's probably not implemented very well, but we see that these details begin to become foggy. So there is room here to explore about, well, what type of reservoir computers are well suited to reservoir time series analysis, which is something that has been researched quite a bit for reservoir computing, but not for unsupervised learning tasks. There's a lot of work that can be done here. The other one we're particularly interested in is this change point detection task, because this is where we really begin to see that, hey, reservoir computing embeddings are particularly helpful here, and we would like to push that into a few more cases. We would love to actually get a application with a less contrived experimental data case, so we can really see where it could find value in a home. But also we want to sort of look at it in the presence of noise and push further sort of this iterative approach to calculating these readouts, because at the moment it is somewhat expensive. So those are just a couple of ideas of where this could be pushed immediately. So thank you. Yeah, so obviously I did skip a lot of details. I didn't really provide many references outside names on the way. If you want the details, if you want references or any of this other information, please reach out to me. I'm happy to discuss it. And yeah, thanks to everyone who's collaborated with me on this, supervisors, former supervisors, and yeah, the Centre for obviously supporting me financially, which makes all of this possible.
So, youth not wasted, maybe? Any questions?
Yep.
So, when you get the change point detection with the complexity there, is it really detecting a change in the complexity immediately, or is it just that the window is now sort of covering two different types of dynamics, so it's now too different to do?
So it's interesting. So we think that it is capturing the complexity. What our argument is that the reason we're seeing, it's probably more evident in this case here, these large spikes we're actually seeing here are because in those transition periods where you are moving from one region to another, it's somehow more complex than either of the individual ones themselves, which sort of makes sense. If we're thinking that what we're really trying to do here is a one-step prediction, and half your signal is a different system to the other half, actually trying to make that prediction is very difficult. So this still does support what we believe the complexity feature is doing. It's just that when we have a window over both regimes, it's a very hard prediction task. Yeah, we do see small variations. Like we can probably see here, this is generally lower than these two. But yeah, the range of parameter values we're seeing here were quite small. So a lot of the variations in the actual complexities they're there, but they are quite small.
Even in Heigo said it's not really hard to distinguish these two. I mean, we color coded it, so I can see it out.
The other one's different from the blue ones, right?
It is actually an abrupt change. It's not like a drift in the parameter, right?
It's an abrupt change in the parameter, but we let the system. Yeah, the window's moving along one step at a time. So yeah, at this point here, it's because we have mostly this with a little bit of this. Yeah. So the actual window I used here was 2,000 points. So it's a significant portion of what we're actually looking at here as well.
It's a logistic map. Can you tell us what the parameter is?
I can tell you their range. I probably couldn't tell you the exact values. So for these ones, I was just looking at a parameter range from 3.7 to 4 to ensure that we're getting this chaotic regime. I believe, if I go back to the bifurcation diagrams, I'll be able to get a better idea. No, not that one, this one. Yeah, So I'm really, yeah, okay, so I'm just looking in this regime here, which is why those changes in the bifurcating parameters are quite
And
small.
you normalised the amplitude at the signal, was it because you know what that normalisation had to do that?
So in that particular case there, what I did is I generated the whole signal and then I,
You just looked at the min and the max and expression of that.
yeah, I looked at the min and max for each section and then did some sort of, yeah.
You don't know analytically what the curve
No,
is.
no, don't know analytically what they are. It was really more just, for the concept of case, we weren't necessarily interested in keeping a lot of these very obvious statistical variations in there. In some way, this sort of, when you
it's a
get the,
little bit harder.
yeah, exactly. Because if you keep the statistical variations in there, one, these methods will be able to detect it trivially, but so will most of the existing statistical methods. So it just was a way of developing one there. You still have interesting dynamics, and it's not so trivial as just sampling.
You just looked at the amplitude adjusted Fourier transform surrogate test page you had just passed. That one, yeah. Why is the Fourier transform test applied to the amplitude adjusted Fourier transform surrogates not completely crap? The 60. Because you're preserving the spectrum.
Yeah, it's a great question. Part of the, so
Isn't the amplitude adjusted parts enough to speed things up?
my belief is it's part of, so this is using the iterative amplitude adjuster. So I imagine in that iterative process there is some small discrepancy, some small error.
You're doing the Schreiber-Schmitz
Yeah,
amplitude adjusted Fourier
yeah, whatever that method is. So while ideally it would perfectly preserve the power spectrum, there is a small discrepancy, and that will lead to essentially finite effects. So I didn't really explain the colouring here, but the idea is anything in this dark blue is statistically insignificant based on the statistical test that we were using.
Yeah, the 60 is bigger than 28
8.
and 8. Yeah,
Well,
that was-
well,
this is,
Ideally, based on how we're doing the random shuffle, we'd actually hope those ones were 0, because you would hope that it is perfectly conserved. So we are still seeing some finite effects in there.
okay.
And since we are on this page, and I heard a rumbling behind me, complaining that you actually don't tell us what the measure is. What is 100? What does the number actually mean?
So, okay.
What are you actually showing?
So this is showing us the number of times out of, so 100 times we are sampling from the two systems and we're comparing the distances. Out of the 100 times we sampled, this is how many times the comparison distance was greater than the reference distance.
Thank you.
You're allowed to ask questions.
I mean, I assume that higher numbers are better.
Yeah. Higher numbers good, brighter colours good.
Tom again.
So you're saying that like as you change the size of the reservoir, like the complexity metric, what was it, the complexity metric that converges to a single thing, so you don't get any variance every
Yeah, so for, yeah, it's for, yeah, so it's for these measures here. So what we found is we did play around with the different height parameters. So we looked at the size, we looked at the regularization parameter as well, and the length of the underlying series. And yeah, what we essentially found is somewhat expectedly longer series, the variance in the measure essentially cuts off. And similarly, we're able to see that for increasing the reservoir size as well. The only variance that remained for increasing the reservoir size was because part of increasing the size is we had to get new adjacency matrices, and that variation was maintained, but we still saw this quite sharp fall off as we increased the size.
I was wondering whether, is there also like a loss in resolution as you make it too large, or make it larger, sorry, right, like, I could imagine, like, maybe the way I'm thinking is, as you make your reservoir larger, right, there's actually a larger amount of it, it's not really doing too much, right, in
Yeah.
terms of prediction, and so like, if you've got one task which is relatively harder than another simpler task, you can sort of heuristically say, well, 90% is doing nothing in either case. So those values will be sort of
Yeah, okay.
unimportant to the prediction. You might even lose resolution in that case for comparing different systems.
At least for comparing chaotic system, periodic system, we didn't really notice that. I'd be interested to see it. We did see some interesting stuff when we were just feeding it with random noise and trying to see what happened with the noise case. That was more, if you've got, say, more nodes than you do time series, it sort of artificially deflates your complexity. And then similarly, yeah, what you essentially see in your noise case is you get this peak when your number of nodes equals your time series, and then as you either have more nodes than time series, you're sort of overfitting and it thinks that it's actually doing better than it is, or if you go too low, it's somewhat everything looks bad, so it doesn't really matter, which might be somewhat related, I think, to what you're talking about there, but at least in terms of comparing periodic chaotic, we didn't really notice anything like that.
But basically, you're still not able to really distinguish between deterministic and random dynamics. Because, I mean, yes, for the mildly chaotic systems that you put on the middle thing, your levels are lower than for the random ones. But if you put something like hyper-chaotic systems in there,
Yeah, it might run into difficulties.
you would most likely get an overlap between the two different
Yeah.
ranges.
Yeah,
So,
potentially. Yeah, but it's, yeah, I imagine, I don't know too much to say about the hyperchaotic, but I imagine that's probably an issue for a lot of data-driven complexity methods on top of those as well.
Yeah, of course,
Yeah.
of course. But I mean, for example, in your paper on the networks, you could just run the motifs and then say, okay, in deterministic ones I see more this, in chaotic random ones I see less of them, which gives you an opportunity to, or the surrogate testing gives you an opportunity to distinguish between random and deterministic dynamics. This one, well, for the systems that you show, and most likely for the reviewer in chaos, it was good enough. But
Yeah, if we wanted to go to the path of being able to actually do, say, surrogate testing and confirm that, we would need probably something a little more sophisticated than what we're doing here. But it does seem to indicate that at least the information is captured somehow in that readout vector. Probably then just comes down to finding a more sophisticated way to
I mean,
read that out.
with that vector, I also feel like, I mean, we already know that we can fit a linear average to it and get, for example, the Lyapunov exponent out of the reservoir computer directly, yeah?
Yeah,
So, of course, somehow if I measure the activation of my network, that I afterwards could average to get directly something like an invariant measure of my, or proxy for an invariant measure of my system. Obviously, it must be in that network as well.
yeah, okay.
You average it, or you look at this activation level or something like this. I'm not surprised that you get the same information out of it.
Yeah, okay.
Yeah. Because if a basic average over it gives you the same result or distinction between it, must be somewhere in there. Okay, one is supervised, one is not supervised, I give you that.
Yeah.
So the fact that this works for your single unit vacuum glass circuits that you designed and built yourself before
Yeah.
faultlessly,
I will say I put that in there somewhat as a motivating example that it would be good to look at other types of reservoir computers. I'm also aware that I did make a small mistake when implementing it, and one of the parameters was way off, so it might have just been operating in a particularly bad regime.
so it's a single, there's one nonlinear node. in this
Yeah,
circuit,
so
right? You've got some delay as well. Is it delayed?
yeah, so it's quite a different system to the network. The idea is, yeah, you do have one node, and what they do is, rather than say try to feed into a large number of nodes, what they do is they time multiplex the input signal. So rather than just having a single value, they've now got a value spread over some time. They feed it through, they then get a time series out, which is that one observation, and then they sample that time series out to then get their one vector. So it is quite a different system, but it's shown quite a lot of success for classification tasks and other areas.
So my hand-wavy argument in favour of reservoir computing for this reservoir time series
Yeah, a lot of the arguments of XNA1 is about getting the delay embedding. But it is there is something more going on than delay embedding as well. I like to lean on the delay embedding because it's a nice result that has now been proven, and it in some way does explain why it is good on dynamical systems, but certainly it is doing more than the delay embedding as well. In some ways, the nonlinearity and the variation in the activations we see is also beneficial, and that is somewhat separate to just the delay embedding.
One last question. You mentioned the very last, on the very last slide that you'd like to get some real data. You are aware that the Centre for Transforming Maintenance and Data Science has access to real data.
And we did try. We did look at some of their data. There was one interesting application which I spent some time on, looking at monitoring wear on sizer teeth, which essentially up on mine sites, they've got these really large machines which they just use for crushing iron ore. These things have really large barrel with teeth on there which turn to crush the ore. And they essentially wanted to know when they were going to wear out. And we thought at some point there might have been an interesting application for something like concept drift, just because actually trying to monitor these things is quite difficult, and trying to do it in real time with their current measures wasn't going to work. But they did have video data which was continuous and did seem to have these drifts between different states. What we found though is that most of the effort was going to be in actually dealing with the video data before we even actually got to applying these methods, which was a big kind of barrier there.
So your answer is you would still like good data, but
Oh,
quality data
if
instead.
if someone knows the best way to process video data, I'd love to talk to you, because I reckon there's still something there, but it would have taken up 90% of the work, and then the concept drift stuff would have been the final 10% max.
Pretty sure that people like Samson might know someone who does video data, if you think about it. Okay, so we are now over time. Thank you very much for the talk.